That is a suggestion.
You can give a wonderful lecture, though.
So today I'm going to give a talk on the convergence of a semi-Lagrangian scheme developed for numerical approximation of Boltzmann-BGK model. This is a joint work of Giovanni Russo and Piero Sondati. So suppose we are given a system of particles, say air around us, or plasma in nuclear fusion reactor, or stars or planets in the universe, and want to extract some physical chemical information from it. And how can we do that? What can you do for it? First, we might try to keep track of the evolution of each particle, for example, by solving Newton's equations of motion. It's, of course, almost impossible considering the extremely large number of particles and extremely complex behavior of particles. Secondly, we may consider the particle system as a fluid and investigate macroscopic variables like density, both velocity, temperature, pressure. This macroscopic approach, of course, is very successful, probably one of the most widely used approach nowadays. But there are cases where this macroscopic approach failed to provide satisfactory description of a system. For example, when the gas is extremely rarefied, or when the configuration lies very far from statistical equilibriums. So, as a compromise, Maxwell and Boltzmann, they decided to study the system statistically. They decided to study how particles are distributed in phase space. So for that purpose, they introduced the velocity distribution function, which is defined by this relation: F times delta x delta v is number of particles and infinitesimal volume around x and v in phase space at time t. This is conceptually almost identical to probability distribution function in probability theory. And they assume that all the relevant important information is encoded in this distribution function. Now our goal reduces to finding out the rules which governs the evolution of this velocity distribution function. And those rules are called kinetic equations. And there are various kinds of kinetic equations depending on chemical or physical hypothesis or hypothesis model, imposed in the modeling. Today we are mostly interested in this model. So for non-ionized and monatomic rarefied gas, non-ionized and monatomic is a fancy way of saying that it's a collection of billiard balls. It's a Boltzmann equation. And this term represents the free transport of particle, non-interacting particle, and this bilinear operator Q captures the effect of collision or interaction. So this equation describes the particle system as a combination of transport and collision. And this collision operator can be written down explicitly as follows. It's a little complicated, and this kappa is a Knudsen number, which is more or less an index on how rarefied is a system, and this pair is post-collisional velocity, and this is a pre-collisional velocity. And the post-collisional velocity can be calculated explicitly from the pre-collisional velocity. So it's very intricate. It has very intricate structure. It's convolution. It involves convolution-like structure. It also involves cancellation structure. It involves fivefold integration, R2 times R3. So it's very hard to develop a fast and efficient deterministic numerical method, usually. And naive application of conventional methods without careful consideration of the fine structure of the operator usually yields poor results, or sometimes devastating results. So far, most widely used methods are probability methods like Monte Carlo method. So it would be very nice if we have an equation which can be computed more easily, relatively easily, but still which mimic the dynamics of Boltzmann equation very closely. So for that purpose, Navarre, Gross, and Krupp proposed this equation called BGK model. This is transport, and what is this? This MF is a local Maxwellian constructed from distribution function as follows. So it's more or less measures the distance from distribution function, and it's a local equilibrium state. So it measures how the particle system lies far from macroscopic or hydrodynamic state. So it's called relaxation operator. So now the complex collision process is replaced by relaxation process. So it's suggested by Navarre, Gross, Krupp. At first I thought it must be Boltzmann and some. And it shares important features with Boltzmann equation, like conservation laws, entropy distribution, and so on. So it has the same system of conservation laws, and it means after scaling, we cannot tell whether it's BGK or Boltzmann, at least in macroscopic level. And it's relatively easy for numerical approximation. It's not easy, but relatively easy compared to the Boltzmann equation. It's a very popular model for numerical tests in kinetic theory. It is known to provide very qualitatively correct results, not quantitatively. So for numerical approximation of this BGK model, this Untitled Seokbae introduced the semi-Lagrangian scheme. Actually, what they proposed was high-order scheme, but here for simplistic proof, we consider the first order version of their scheme. Here the F tilde is something like this. So suppose we constructed the discrete values at n time step. example, we start from here. Let this node be xi bj node. And here we trace back along discrete characteristic to reach the previous time step. And almost surely you never reach the node exactly. So to know the value here, we need some kind of interpolation. In this case, we use the simplest interpolation, linear interpolation. So that's the definition of this f tilde. So this is a linear reconstruction of this value. And this Nij is discretized local Maxwellian. Let's briefly overview how this scheme was derived. So first we discretize the transport part using semi-Lagrangian formulation, and how to treat the relaxation part. First, let's try explicit method. It's explicitly computable, so it's very fast. Once you know the end step, then you know the next step. But it's well known that we should impose very restrictive stability conditions like CFLs or something. And what about the implicit method? The stability of implicit method is known to be very good, but it's more expensive, that we should solve some big metrics. So what should we choose? Hopefully we want, everybody wants their scheme to be stable and it involves low computational cost. The stability in this case is especially important because for kinetic equations in small Knudsen number regime, it involves some stiffness issues. It causes some. So they decide to choose somewhere in the middle. So this part is treated as implicitly, but this part is not explicitly, not implicitly. So if you're lucky, only good things will happen. If you're not, only bad things will happen. Nobody knows until they run a computer and wait until it shows the results. And it performs very well. Efficient, fast, stable. So some natural mathematical questions. Will it converge? Or if it converges, in what space should we measure it? And what would be the convergence rate? So we obtain some affirmative result. So here is our first result. So suppose that the initial data is bounded, the weighted L infinity norm of weighted at infinity sublevel norm of initial data is bounded and need not be small. And we impose some smallness assumptions of mesh size with respect to the initial data and the final time. Then we have this convergence estimate. Is this 1 over delta t term looks a little unsatisfactory, and we'll come back to this issue later. This R is the domain of velocity for kinetic equations is the whole Rn space. So for numerical computation, we should cut somewhere off. So this R shows where we cut it. And the existence result under this condition is established by Pertham, covariancy, and regularity issued by Tier. And this is a local theory. They established local existence result of smooth solution. It's like, so whether it can be extended to global result also seems to be an interesting question. And local theory is unsatisfactory, of course, but it's okay in this case because you never run a computer forever. So let's briefly overview sketch of proof. So we extend the discrete values to the whole numerical domain. It's conceptually very elementary. So we have discrete values in X, then we connect them by line. And we have values in B, we connect them by piecewise constant function. In this way, we extend the discrete distribution function to the whole numerical space. And the reason why we're doing this is, in this formulation, we can treat the continuous distribution function and discrete distribution function in the same framework, and it helps. When we extend the macroscopic fields, similarly like this. And the scheme can be reformulated as follows after the extension. Now, it looks very different from the BGK model. So we decided to transform the BGK model so that it looks very similar to the scheme. This is obtained by applying Taylor's theorem to Mach form at this point and that point in base space, and apply some tedious calculation. There are interesting, exciting calculations, very tedious calculations. This is tedious calculation. Now since this and this look very similar, so now we can do something. We subtract the reformulated scheme from consistent form and take L12 norm to obtain this kind of inequality. Now this is a remainder term. Why we used L12 norm? It's very natural. First, it's very natural that it corresponds to mass plus energy for the Kinetic equations. And of course, and if it were just natural but not useful, we would not have used it. Being that is natural, the fact that it's natural actually helps very much in obtaining useful estimates and reduce much calculations. So in this norm, we obtain many estimates like the continuity of Maxwellian Sobolev type estimates, and estimates for differences of discrete distribution functions, estimates for differences of discrete local Maxwellians, and estimates for remainder terms. And we also need some estimates in weighted L infinity Sobolev norm. So in this norm, we obtain some norm preserving property control of. We could control the local Maxwellian in this norm and the stability of the scheme. But this vector would have ended the proof if this were a linear scheme by Locke's equivalence theorem. But this is a nonlinear scheme. And this was the most difficult part in the proof, to obtain lower bound estimate of discrete macroscopic fields. And we put all these estimates, all these 3 pages of estimates, into here. To obtain a relation between the n plus first error and the nth error, plus some additional remainder term. And then we iterate this inequality until we get to the ground. And here, this 1 over delta t term arises, because we should sum the geometric series whose ratio is this. So as we've learned in high school, it involves this term. I'm sorry, somebody learned this elementary school or middle school. I learned it in high school. I didn't know that until I graduated middle school. So we have problematic term. So at first I was very unhappy, and I looked through references, the other papers on convergence of semi-Lagrangian scheme for other equations. And this 1 over delta t term was like ubiquitous. They all have these terms. So it makes me a little happy, but still, I'm not sure whether this 1 over delta t can be removed by applying more careful analysis, or is in some sense generic. I think I should work on it more. Oh, it's here. Oh, I typed it. I forgot. And in principle, initial data can be approximated in any order, but since we are considering first order method, we assume that it's approximated in first order, and we adjust some constants to complete the proof. So, as far as I know, this is the first result on strong convergence of fully discretized scheme for nonlinear collisional kinetic equations. But there are some results for other equations like parabolic types or velocity types, and all of their estimates have 1 over delta t term in their estimates. So maybe it seems to be generic, but I don't know. I think I should work on it more further. Next, we move to another result. It's on the perturbed BGK model or linearized BGK model. We linearized the BGK model around global Maxwellian and obtained this perturbed equation. This is a linear term, and this is perturbation. Oh, this EI is orthogonal basis of the kernel of macroscopic projection. And this term looks a little complicated, but anyway can be controlled under the assumption of small energy. So we established global existence results and established asymptotic behavior, exponentially decaying. The main theoretical tool, technical tool was nonlinear energy method developed by Yang Guo, who is an advisor of Professor Henry Wang. And for this perturbed BGK model, of course, we can design a semi-Lagrangian scheme, and we could obtain a similar result under almost similar hypothesis, like this. Again, 1 over delta t term. I hate it, but so research plan. Let me briefly review what research plan. So, will it be possible to remove it, or is it generic? I don't know. I'll try. And here we assume that the collision frequency is constant for simplistic proof. Thank you. In which case the collision frequency reduces to Knudsen number. But there are more physically relevant models which has non-trivial collision frequencies. Tried calculation for some of them, and it seems that our framework work with slight modification for these non-trivial collision frequencies. And the real challenge seems to be obtain convergence estimate of higher order schemes, which they actually used for computation. It involves some, diagonally implicit BGK method and so on. And for the high order method, we expect to obtain this kind of high order convergence rate. In that case, if the size of delta V, delta X, and delta T are comparable, then the delta T can be observed here, and we don't need to worry about it anymore. But for our first order result, this 1 over delta T looks really ugly, actually. And there's also Aoki and Pratham recently proposed BGK model for gas mixture. So I also think that our framework can be applied to this setting with some modification. So this is all I prepared today, and thank you very much.
Are there any questions?